We're at the top of page 3. The triangle that you created on page 2 with the coefficients, that is what we call Pascal's triangle. It's named after the French mathematician Blaise Pascal. He started using it in the 17th century for some very lovely patterns. But actually, Persian and Asian cultures have been known to use it since the early 13th century-ish, around there. That's on the internet if you want to look it up some more. All right, so there are many, many patterns in Pascal's triangle. One such pattern, the numbers in each row, allows us to quickly expand a binomial raised to any whole number exponent. So if you haven't figured out the pattern yet, if you look at the row above, 1 plus 1 gives us that 2. Okay. 1 plus 2 gives us this 3 here. 2 plus 1 gives us this 3 here. And then 3 plus 1 gives us 4. 3 plus 3 gives us 6. 1 plus 3 gives us 4, etc. Okay. So we always add the two numbers in the row above to get the number in the row below, if that makes any sense. All right, so I just wrote that down over here. Here, n equals 0, n equals 1, n equals 2. That refers to the row numbers. I'm going to write that at the top here. So the very first row of Pascal's triangle is not the first row. It's called the n equals 0 row. All right, and if you notice here, the row number will always coincide with the second term in that row of Pascal's triangle. All right, so easy to remember. Try to figure out the numbers in row n equals 6 and n equals 7. So pause the video and come back to it. And here are rows n equals 6 and n equals 7. And as you can see, this pattern would continue on forever and ever and ever. And the nice thing about this pattern is the first half of the row is just mirrored in the next half. Okay? If it's an even numbered row, there's going to be an odd number of terms. And if it's an odd numbered row, then there's going to be an even number of terms, because if you remember from the previous example, we always had the row number plus 1 terms. I'm going to write that down. Beyond the pattern of just being able to figure out what the next number is, there are so many other patterns. We just can't get into it though because we're kind of running out of time in this course. So instead, we're just going to use the information given to us in each of these rows to help us expand binomials really quickly without having to manually distribute everything and collect all the like terms or anything like that. So let's fill out this summary chart. Binomial expansion using Pascal's triangle. The expansion of a plus b to the exponent k is always going to have k plus 1 terms. So if the exponent is 4, then a plus b to the exponent 4, you're going to end up with 5 terms in the end. The first term of the expansion a plus b to the exponent k is a to the 0, b to the k. And the last term is, actually I'm going to just fix that, hold on one second. I'm just going to switch around the order of those exponents, my apologies. A, k, b, 0, not that it really matters, anyway. And the last term is a0 and b to the exponent k. The exponent of a is going to start at k, and then it's going to decrease by 1 going from left to right. The exponent of b is going to start at 0, and then it's going to increase by 1 up to k, going from left to right. The exponent sum or degree of each term is going to equal k. So if you remember in the n equals 4 row, all of the exponent sums were 4. And the coefficients of the terms can be obtained from the n equals kth row of Pascal's triangle. So in the next video, I'm going to go over in more detail how to expand a binomial just using these patterns from Pascal's triangle, and give you an opportunity to practice as well.